Swayam Prabha. Digital India. Educated India.
Welcome back. So, already we have seen a couple of numerical problems on the earth pressure theory in the last lecture, and today we will be solving few more numerical problems on the earth pressure theory of soil. And basically you will be getting the idea that how you can solve the different problems related to the earth pressure theory in soil. Okay. So, let us write down the problem. For the retaining wall as shown in figure, plot the distribution of active earth pressure and determine the magnitude and point of application of the resultant active thrust. Okay. So, let us draw the figure first. This is your point A, this is the retaining wall. Okay. You have 3 layers of soil, this is point B, this is point C, and this is point D. Okay. This is your loose sand, gamma equal to 16.4 kilonewton per meter cube and phi equal to 25 degree. So, this is your groundwater table is here at this level. So, let me write down the depths. This is say 1 meter, this is 1.2 meter, and this is 2.3 meter. This is also loose sand, where gamma saturated equal to 18 kilonewton per meter cube and phi equal to 22 degree, and this is your dense sand, gamma saturated equal to 20.5 kilonewton per meter cube and phi equal to 32 degree. So, this is the problem. Okay. So, you have the retaining wall like this, okay, and you have 3 layers of backfill. The first layer is having loose sand, that is the top layer is having loose sand, which is having the depth of 1 meter, and this loose sand is having the unit weight 16.4 kilonewton per meter cube and phi equal 25 degree, and here is the groundwater table, that means groundwater table is at 1 meter below the ground level, and second layer is also loose sand, that is stratum 2 is also loose sand, and that is having gamma saturated equal to 18 kilonewton per meter cube and phi equal to 22 degree. Whereas the third layer, that is the stratum 3, it is having dense sand and which is having gamma saturated equal to 20.5 degree 5 kilonewton per meter cube and phi equal to 32 degree. Okay. So, and you need to find out that first one is the plot the distribution of active earth pressure and determine the magnitude and point of application of the resultant active thrust. So, first we will find out the distribution of the active earth pressure, and from the distribution we can find out the resultant active thrust as well as the point of application. Okay. So, let us solve this problem. So, active pressure exerted by various strata are as follows. First one is stratum 1, okay. So, where your first we need to calculate the magnitude of coefficient of active earth pressure coefficient for first stratum. So, Ka1 which is defined by 1 minus sin phi 1, where is phi 1? Phi 1 is 25 degree by 1 plus sin 25 degree, that comes as 0.406. Okay. Now, what is the pressure at point A? What is point A? Point A is at the top of the wall. So, what is the pressure? What is the active earth pressure at point A? That is 0, right? Fine. Now, what is the pressure at point B when you are considering stratum 1? Please remember, because at point B you are having the interface between stratum 1 and stratum 2. That means, when you are within stratum 1, at that time you will be getting some pressure at point B, and when you are considering stratum 2, at that time also you will be getting some pressure at point B. So, basically at the interface you will be getting some jump, right. Already discontinuity already we have seen in some problem in the last class. Okay. So, Pb is nothing but Ka1 gamma 1 and H1, that comes as 0.406 multiplied by gamma 1 is 16.4 multiplied by H1 is, that is the depth of stratum 1 is 1 meter. So, that comes as 6.7 kilonewton per meter square. So, we can plot this distribution. So, this is your different points, point A, this is your point B, this is your point C, and this is your say point D. Okay. So, from this whatever calculation we have done so far, based on that, what is the pressure at point A? Pa is 0. So, that is 0 here. Okay. And what is the pressure at point B when you are considering stratum 1? That is coming as 6.7 kilonewton per meter square. So, I will be getting linear distribution, and this is my say 6.7. So, I am not writing kilonewton per meter square everywhere, because it will be congested, then the figure will be congested. So, I am writing only the numerical value. However, all numerical values will be having the unit of kilonewton per meter square. Okay. Now, we are going to calculate stratum 2. Okay. This stratum is fully submerged while computing the active earth pressure in this region stratum 1 is to be treated as a uniform surcharge of intensity Q, where say Q1, where Q1 is equal to gamma 1 H1, that is nothing but 16.4 is the gamma 1, that is the unit weight of the stratum 1, and depth of stratum 1 is 1. So, it comes as 16.4 kilonewton per meter square. Now, what does it mean? So, when you are considering stratum 2, so basically the active earth pressure in this region in stratum 2, when you are finding out, stratum 1 is to be treated as a uniform surcharge of intensity Q. That means, when you are considering stratum 2 is spanning from point B to point C, right. So, at point B, whatever you will be getting, or I mean at point C or point B or in between whatever point you are considering in stratum 2, basically this stratum 1 will be giving you some uniform surcharge loading, okay, on top of that point, right. So, that will be always there. Okay. So, when you are considering stratum 2 basically, so the stratum 1 will be considered as the uniform surcharge which is acting on that particular stratum. Okay. So, that Q1, that uniform surcharge is nothing but gamma 1 into H1, that is the complete surcharge, that is the total depth of stratum 1, okay, which is lying over the stratum 2. So, that will be considered as surcharge, and that is given by 16.4 kilonewton per meter square. Okay. So, now I can find out other parameters like Ka2, that means active earth pressure coefficient for stratum 2, which is 1 minus sin 22 degree by 1 plus sin 22 degree, it comes as 0.455. So, Pb, that means active earth pressure at B, but when you are in stratum 2, that means the point B is a crucial point. Point B is the interface between stratum 1 and stratum 2. So, you have got some pressure, what is that, 6.7 kilonewton per meter square at point B when you are considering stratum 1, that means when you are coming from point A to B. And now, when you are starting from point B to C, then also you are getting some pressure at point B, and that pressure we are now going to calculate, because you are now considering stratum 2 under consideration. Okay. So, Pb is equal to Ka2 into Q1, simple, because you have the surcharge, and that is surcharge is nothing but the vertical pressure. So, the lateral pressure will be Ka into that surcharge amount. Okay. So, Ka2 into Q1, which is 0.455. Now, what is Q1? Already we have calculated 16.4, that comes as 7.5 kilonewton per meter square. So, you are getting some jump at point B, right, from 6.7 to 7.5 when you are considering from when you are travelling from stratum 1 to stratum 2, you are getting this discontinuity and the jump. And what is PC? So, please remember point C is also another interface between stratum 2 and stratum 3. So, we will be analyzing this thing very similar way. That means, now we are considering stratum 2. So, we will be getting one pressure component at point C when we are considering stratum 2. Now, similarly, when you will be considering stratum 3, at that time also we will be getting some jump or some pressure component at point C. So, that will give me the discontinuity. Okay. So, PC is equal to, how I can calculate, Ka2 into Q1, that will be there, plus Ka2 gamma 2 prime means the submerged unit weight, because you see that groundwater table is at this level, right. At this level you have the groundwater table. So, anything which comes below point B will be completely submerged condition. Okay. So, therefore, we have to use gamma 2 prime instead of gamma 2 or gamma saturated, whatever I have got in the problem. So, gamma 2 prime into H2, is that okay, or is that all? No, right. So, you will be getting some other parameters or some other component which will be coming completely based on the water pressure, that is because hydrostatic pressure, right. So, water is there. So, that part will be coming as gamma W into H2. So, this is the lateral active earth pressure at point C when you are considering stratum 2 itself. Okay. So, we can calculate this. This is 7.5, already we have calculated, okay, plus Ka2 is 0.455, gamma 2 prime. So, how I can find out gamma 2 prime? I have gamma saturated, right. So, gamma saturated minus gamma W will be equal to gamma prime, that is gamma submerged. So, gamma saturated is given as 18 if you look at the problem, and gamma W we are considering 10 kilonewton per meter square meter cube, and H2 is 1.2, that is the depth of stratum 2, plus water 10, gamma W is 10 and H2 is 1.2. So, from this I can get 7.5 plus 4.4 plus 12. So, total is coming 23.9 kilonewton per meter square. Now, come back to the plot. So, at point B, what you are getting when you are considering stratum 2? It is 7.5. So, say this is your point 7.5. So, you are getting some jump, okay, 7.5, and it is ending at 23.9, total is 23.9 at point C. That means, at this level you will be getting total as 23.9. Out of 23.9, 7.5 is there, 4.4 is coming from stratum 2 itself, and 12 is coming from water. So, your plot will be so this is your 7.5, this is your 4.4, and this is your 12. Okay. So, you have got the pressure distribution like this. Now, what we can do, we can find out the pressure distribution considering stratum 3. Now, if we consider stratum 3, so equivalent surcharge as before, we can calculate surcharge due to stratum 1 and stratum 2. Now, when you are considering stratum 3, basically your equivalent surcharge, that means on top of this stratum 3, what are the layers lying? The stratum 2 and stratum 1 both are lying on top of your stratum 3. So, that will be acting as a surcharge component. So, equivalent surcharge will be Q2, which can be calculated as gamma 1 H1 plus gamma 2 prime H2, where gamma 1 is the unit weight of stratum 1, H1 is the depth of stratum 1, and gamma 2 prime is the submerged unit weight of stratum 2, and H2 is the depth of stratum 2. So, that will be acting as a uniform surcharge on top of stratum 3. So, I will be getting from this 16.4 into 1 plus 18 minus 10 will be your gamma 2 prime into 1.2, which comes as 26.0 kilonewton per meter square. Okay. Now, I can calculate other components, required components Ka3, which is nothing but 1 minus sin 32 degree by 1 plus sin 32 degree, which comes as 0.307. So, therefore, Pc, again you will be getting Pc. So, you will be getting the jump now. So, Pc will be equal to what? Ka3 Q2 plus gamma W H2, that will be coming due to the water, because now water is there. Okay. So, Ka3 into Q2, that will be the lateral pressure due to the surcharge, the uniform equivalent surcharge, whatever you have calculated just now, plus gamma W into H2 will be nothing but the water pressure at that level. Okay. So, which will be equal to 0.307 into Q2 is 26 plus gamma W is 10 and H2 is 1.2, that comes as 8 plus 12, which will be equal to 20 kilonewton per meter square. Okay. So, how we can plot this? I will come back that thing later on. So, first we will calculate PD. So, PD is Pc plus Ka3 gamma 3 prime H3 plus water pressure gamma W H3. Please try to understand. So, Pc will be always there, right. So, whatever you have calculated just now, this 20 will be there, plus Ka3 into gamma 3 prime. What is gamma 3 prime? That is the submerged unit weight of stratum 3 into H3. H3 is depth of stratum 3 plus the water pressure at that level, right. So, D is the bottommost point of the wall. So, that gives me 20 plus 0.307 into gamma 3 prime is equal to 20.5 minus 10. What is H3? 2.3 plus 10 into 2.3, that comes as 20 plus 7.4 plus 23 is equal to 50.4 kilonewton per meter square. So, if I plot that thing here, so what you are getting? Earlier your Pc was, when you considered stratum 2, at that time Pc was 23.9, 7.5 plus 4.4 plus 12. Now, when you are considering stratum 3, at that time what you are getting? Pc is equal to 20, that means you are getting some reduction. So, discontinuity obviously, but all the times it will be increasing, that is not necessary. So, here actually you have got the increase 6.7, it has got increased to 7.5, but it may not be true always. So, whatever we are seeing now for stratum 3 actually, okay, when you are considering point C, so coming back from stratum 2 to stratum 3, at that time at the interface you are getting 23.9, but you are, when you are considering stratum 3 itself, you are getting the pressure, active earth pressure at point C is 20. So, you are getting some reduction. So, say this is point say 20. So, this is my 20 say. Okay. Now, from there you are getting this and you are getting this. So, this is your 7.4 and this is your 23. Okay. So, this is the distribution, this is the distribution of active earth pressure. So, please be careful when you are solving this type of problem. Okay. So, once you get the distribution, now you can find out the different thrust for different say area, and you can add them together to get the resultant thrust, and finally you can find out the point of application. So, getting distribution itself is a big deal. So, once you have got this distribution, then other things will be very simple. Now, basically this part we are calling the force is due to this triangular area, top triangular area is say P1, then this rectangular area say P2, then this triangular area say P3, and this triangular area say P4, then this rectangular area say P5, this triangular area say P6, and this triangular area say P7. Now, our job is to find out P1 to P7. Okay. Now, let us see how we can find out that. So, we can calculate all the forces now. Say P1, how we can calculate P1? So, I can write down this is your 2.3 meter, this is your 1.2 meter, this is your 1 meter. So, P1 is how much? P1 is 0.5, that is the area of triangle, 0.5 into 1, that is the height, into 6.7, which comes as 3.35 kilonewton per meter run, kilonewton per meter run of the wall, because normal to the board you are having infinite length of the wall. So, that is the plane strain problem or 2D problem. Anyway, so this is your P1, I hope you have understood. So, 0.5 into 1, that is the height, and 6.7 is the base. So, that gives me 3.35 kilonewton per meter run of the wall. So, that load or the thrust is P1. Okay. And where it is acting from the base, if I say that is Y1, where it is acting 2.3 plus 1.2 plus 1 by 3. Okay. That means 2.3 plus 1.2 is equal to 3.5 plus 1 by 3, which comes as 3.83 meter. Similarly, I can calculate P2, which is nothing but the area of this rectangle, okay, this rectangle. So, P2 is nothing but 1.2 into 7.5, that comes as 9 kilonewton per meter run. Where it is acting? Y2, 2.3 plus 1.2 by 2, okay, 2.3 plus 1.2 by 2, that comes as 2.9 meter. Now, coming to P3. P3 again is a triangular distribution. Okay. So, 0.5 into height is 1.2 and base is 4.4, that gives me 2.64 kilonewton per meter run, and where it is acting Y3. Now, look at this plot, Y3 will be 2.3 plus 1.2 by 3, right, 2.3 plus 1.2 by 3, that comes as 2.7 meter. Similarly, I can calculate P4. P4 again, that is due to the water, again it is triangular distribution. So, I can write 0.5 into 1.2 into base is 12. So, that gives me 7.2 kilonewton per meter run, and Y4 is equal to same, right, 2.3 plus 1.2 by 3 is equal to 2.7 meter. Now, coming back to P5. What is P5? P5 is the area under this rectangle, entire rectangle, right. So, P5 is nothing but 2.3 multiplied by 20, that gives me 46. And what is Y5? Y5 will be simply 2.3 by 2, 2.3 by 2, which is equal to 1.15 meter. Then P6, that is triangular distribution. So, that is nothing but 0.5 into 2.3 into 7.4, which is equal to 8.51, and Y6 is equal to what, 2.3 by 3, 2.3 by 3, which is equal to 0.77 meter. Now, coming to P7. P7 is this triangle, last triangle, okay, due to the water. So, that is again 0.5 into 2.3 into what is the base, 23, that gives me 26.45 kilonewton per meter run. Okay. Now, what is Y7? That is same, 2.3 by 3, which is nothing but. So, you have calculated all the forces. Okay. So, now this is the exercise you have to do once you have got the distribution. Unless until you get the distribution, you will not be able to find out this thing. Okay. Or if you want to find out all those things, you will be doing the mistake. Without plotting, without getting the distribution, do not go for this type of calculation, because you will be getting, I mean, error, or you will be getting mistake. That is quite obvious, because you will be forgetting to consider some force, some thrust, or something like that. Because unless until you get the distribution like this, you will not be getting the proper discontinuity or the jump condition. So, you may do the mistake in calculation of the forces. So, it is always better to go for plot or the distribution, and then you go for this type of calculation. So, your total active thrust will be how much? Summation of I is equal to 1 to n pi. So, pi is P1 to P7. So, that gives me, if you add them, 103.15 kilonewton per meter run. So, this is your PA. This is the resultant thrust. So, whenever you are asked to find out the resultant thrust, you have to calculate like this. Okay. So, this is the total thrust, active thrust on the wall. Now, what is the point of application of this thrust? So, point of application, if I want to find out y bar, that means from the base. So, y1 to y7 everything is measured from the base of the wall. So, y bar is also from the base of the wall. So, that means if I want to find out that PA, say this is my PA and this is my y bar. Okay. So, y bar is equal to summation of Pi yi by summation of Pi. That gives me, if you do this 145.3, I am not writing all the values, you can check it, which comes as 1.409 meter. So, this is your 1.409 y bar is equal to. Okay. So, you can write here actually that the total thrust is coming as 103.15. So, hence the resultant active thrust of 103.15 kilonewton per meter run is applied at 1.409 meter above the base of the wall. Okay. So, this is the problem. So, you have solved very critical problem, okay. And you look at the distribution, getting this distribution is not so easy. Okay. So, you have to understand the concept properly, and based on that you calculate step by step to get the pressure at the interfaces, and then you get the distribution. Okay. Now, we will go to the next problem. So, next problem says a retaining wall with a smooth vertical back face So, when you are considering smooth vertical back face, basically your Rankine's theory holds good. So, smooth vertical back face has to retain a backfill of C5 soil up to 5 meter above the ground level, okay, above GL. The surface of the backfill is horizontal and it has the following properties. Such as gamma equal to 18 kilonewton per meter cube, C equal to 15 kilonewton per meter square, and phi equal to 12 degree. Then plot, first one is plot the distribution of active earth pressure on the wall plot the distribution of active earth pressure on the wall. Second is determine the magnitude and point of application of active thrust. Third is determine the depth of the zone of tension cracks. Fourth one is determine the intensity of a fictitious uniform surcharge which, if placed over the backfill, can prevent the formation of tension cracks, can prevent the formation of tension cracks. And number 5 is compute the resultant active thrust after placing the surcharge. Okay. So, this is your problem. So, now let us solve this problem. Now, solution: for a C5 soil, the intensity of active earth pressure at any depth z is given by what? You know that, right? Already we have discussed this thing in the lecture, right? So, that active earth pressure is Pa is equal to gamma z by n phi minus 2c by root over n phi, right. This is the active earth pressure intensity at any depth z in C5 soil, is not it. So, Now, here your n phi is nothing but tan square 45 degree plus phi by 2. So, which comes as 1.525, and we can calculate for our ready reference root over n phi is 1.235. So, at the top of the wall, that means Z equal to 0. What is your active earth pressure? Say at that point we are defining as say point A, at the top of the wall say A. Okay. That means Z equal to 0, that PA active earth pressure is given by, because this part will be becoming 0 because Z is 0. So, gamma Z by n phi will be 0. So, remaining part will be minus 2C by root over n phi. So, where I can write minus 2 into 15 by 1.235, which gives me minus 24.3 kilonewton per meter square. Now, at the base of the wall, say point B, that means Z equal to 5 meter. At that time, what will be your active earth pressure? PB is equal to gamma Z is now H, right. So, gamma into 5 meter is your Z. So, at the base of the wall. So, 18 into 5 divided by 1.525 minus 2 into 15 divided by 1.235 equal to 34.7 kilonewton per meter square. That means, we have got the active earth pressure at the top of the wall as well as the base of the wall. So, we know two coordinates. That means, if this is the wall, total depth of the wall, okay. So, I know this is my 24.3 minus, and this I know this is 34.7 plus kilonewton per meter square. This is also kilonewton per meter square. Okay. Now, I can join this two. Now, you can do this graphically as well as analytically. Graphically means you plot this thing graphically. So, all those things, all those coordinates will be plotted graphically, and you join these two lines, and then you find out what is the depth where this active earth pressure is becoming 0, or else you can find out that thing from your previous knowledge, that is Z naught, right. So, the depth of zone of tension crack is given by so we are not going for graphically. So, we are just calculating this thing is given by what? Z naught is how much? Do you remember? Z naught is 2C root over n phi by gamma, 2C root over n phi by gamma. So, what is Z naught? Z naught is this depth, right. So, that is coming as, if you put all the values, 2 into 15 into 1.235 by say gamma 18 it comes as 2.06 meter. So, this is your 2.06 meter and remaining part will be 2.94 meter. Okay. So, let us this point as a small a, b and c. So, this is the positive pressure, that means compressive thrust or the push, okay, and top part will be under tension. Okay. So, once we have got Z naught, we can calculate the resultant active thrust. The resultant active thrust is given by the resultant active thrust is given by the part A, B, C of the pressure distribution diagram, isn't it? So, that is the total resultant active thrust. Already we considered that thing, that we will not, this is the total resultant active thrust which is acting on the wall. So, if we have the tension tag, then this part will be completely ignored, right. So, once this part is ignored, then this whole area will be acting as the total thrust on the wall. So, that is coming as P A is half into 2.94 into 34.7 is equal to 51 kilonewton per meter run. Okay. And the point of application, the point of application of PA is located at 2.94 by 3, that is 0.98 meter above the base of the wall. Okay. So, these things will cover the first three part of the problem. Okay. So, these things will cover first three part of the problem. So, the first three parts of the problem we have covered just now. So, the maximum negative pressure intensity developed at the top of the wall equal to minus 24.3 kilonewton per meter square. Already we have seen that, already we have calculated and we have seen that. Evidently, the formation of tension cracks can be prevented by placing a surcharge Q on the backfill which can neutralize this negative pressure. So, what does it mean? The maximum negative pressure intensity developed at the top of the wall is coming as minus 0.24.3 kilonewton per meter square, that already we have got it. Now, the formation of tension cracks can be prevented. I mean, see how you will prevent the formation of the tension cracks. That means, if you do not have any tension at the top at the top of the wall, then you will not be getting any tension crack. Because of tension only you will be getting the tension cracks. Now, somehow if you manage to get that 0 negative pressure, then you will not be getting any tension crack. So, that says the formation of tension cracks can be prevented by placing a surcharge Q on the backfill which can neutralize this negative pressure. So, if you apply some predetermined or prefixed some surcharge on top of the backfill, then basically that will neutralize this negative pressure, and ultimately you will be getting 0 pressure at the top of the wall and it will be increasing. So, if that situation happens due to the application of this kind of fictitious surcharge, then we can get rid of, or we can avoid this kind of negative pressure generation at the top of the wall, right. So, now after placing the surcharge Q the vertical stress sigma V at any depth Z is given by sigma V equal to Q plus gamma into Z. Agreed? Q is the surcharge. I do not know what is the value of Q. I need to find out that Q which can utilize this negative pressure generation. Okay. So, Q plus gamma Z is nothing but the vertical stress at any depth Z. So, therefore, the active earth pressure at point A, that is at the top of the wall, is nothing but Q plus gamma Z n phi minus 2 c root over n phi. Am I right? So, instead of gamma Z, now you are having Q, this term is coming as additional term. So, at point A means at Z equal to 0, at the time this term will be going to be 0. So, you will be remaining part will be so your PA at Z equal to 0 will be what? Q by n phi minus 2 c by root over n phi. Now, why you are putting Q? Why or what is the purpose of putting this Q? To get rid of this negative pressure generation or development of negative pressure. That means, how you will get rid of negative pressure? That means, there is no negative pressure at the top of the wall. That means, from top of the wall to some depth Z naught, basically we are getting the negative pressure. If that negative pressure has to be avoided, then what to do? That Q or that PA, that means the pressure, active earth pressure at Z equal to 0 must be 0, and then it should increase monotonously with the linear variation. So, in that way we can avoid the development of negative pressure. So, but the magnitude of Q is such that at Z equal to 0 active earth pressure is 0, right. This is the condition for applying Q. After application of Q, I will be getting the pressure, active earth pressure at point A, that is at top of the wall, is 0. So, if that is true, I can write down Q by n phi minus 2 c root over n phi is 0, which gives me Q equal to 2 c root over n phi. By putting all these values, I will be getting Q equal to 37 kilonewton per meter square. So, again at z equal to h, your Pb, that means at the base of the wall, Pb is nothing but Q plus gamma h divided by n phi minus 2 c root over n phi. By putting all the values, 37 plus 18 into 5 divided by 1.525 minus 2 into 15 by 1.235, which gives me 59 kilonewton per meter square. So, therefore, the pressure distribution will look like, say this is my total depth of the wall, so this was negative 24.3. Okay. So, earlier it was like that, right. Now, after putting the surcharge, I will be getting, this is my pressure distribution. This is your 24.3, which is getting neutralized by this surcharge, and this is 34.7, and total is coming 59. Understood? So, this negative part we are able to avoid by putting this fictitious surcharge, or that whatever uniform surcharge we are putting. So, we are, if we put 37 kilonewton per meter square on top of the backfill, we will not be getting any tension crack. So, tension crack can be avoided by putting this kind of surcharge. So, the resultant active thrust in this case is given by PA is equal to 0.5 into 5 meter into 59, because now you do not have any kind of tension, the complete compression, complete thrust, because this is the pressure distribution now. Okay. So, that gives me 147.5 kilonewton per meter square applied at a height of 5/3, that is nothing but 1.67 meter above the base. Okay. I hope you have understood this problem. This problem was very interesting problem. How to get rid of tension cracks, right? By putting this surcharge, you can get rid of tension, because you are neutralizing the tension whatever is getting developed at the top of the wall. Okay. So, I will stop here today. So, in the next lecture, we will be taking few more numerical problems. Okay. Thank you very much.